Hello everyone, this is Lakshmi. Welcome to my channel Lakshmi Lucky. Okay, we are discussing BSc final year linear algebra subject. So previous question paper we are discussing January 2023 right now. So in that part B, second problem, find spanning set for the null space of matrix A is equal to -3, 6, 1, 1, -7, 1, -2, 2, 3, -1, 2, -4, 5, 8, -4. This matrix has given so we'll find the spanning set of null space of matrix A is. Okay. So here given matrix A is equal to, this one is there, -3, 6, 1, 1, -7, 1, -2, 2, 3, -1, 2, -4, 5, 8, -4 right now. So here to find the spanning set for the null space of A, first we need to reduce the matrix A into echelon form. Okay. So here by using echelon form is nothing but by using in the first row first element, we need to make corresponding these two elements should be zeros. Okay. So I am changing here R2 and R3. R2 is nothing but second row, R3 is third row. Okay. So R2 to R2 I am multiplying with 3 and R3 is plus R1 we can do, and R3 also 3R2 plus 2R1. Okay. Then after 3R2 means 3 ones are 3. 3 minus 3 is 0. 3 twos are 6. Minus 6 plus 6 is 0. And 3 twos are 6 plus 1, 7. And 3 threes are 9. 9 plus 1, 10. And 3 into -1, -3, -7, -10. Okay. And same as R3 also, third row. Here we are multiplying R3 with 3 because R3 we have 3 no. So 3 R3 means 3 twos are 6 and 2 threes are 6. -6 plus 6, it should become 0. And 3 fours are 12, -12, and 2 6 are 12 plus 12, it should become 0. And 3 fives are 15 plus 2. 15 plus 2 is 17. 3 eights are 24 and 2 ones are 2. 24 plus 2, 26. And 3 fours are 12. -12 plus 2 sevens are 14. -14 -12 -26. Okay. So after reducing the given matrix, we are getting this one. Okay. We'll take B is nothing but we got no this matrix you should take So after consider the null space condition. By the definition of null space, Ax equal to 0. Here we are taking this matrix after reducing we are getting that matrix no, that is we are taking B. So Bx equal to 0 we can take, where x is nothing but x1, x2, x3, x4, x5, because here elements are 5 are there, 1, 2, 3, 4, 5. So that's what we are taking, x1, x2, x3, x4 and x5. Okay. Bx equal to 0 means B, we have this matrix into x. This matrix is equal to 0 matrix, 0, 0, 0. Because 3 rows are there, that's what 3 zeros you should take in column wise. Then after you should multiply, matrix multiplication, -3 into x1, -3x1 plus 6x2 plus x3 plus x4 -7 into x5 is equal to 0. Make that equation 1. And 0 x1, 0 into x1 is 0, 0 into x2 is 0, 7 into x3 is 7x3 plus 10 into x4, 10x4 minus 10, x5 is equal to 0. That is, we'll take equation 2. And in the third row also same, 17x3 because x1, x2 should become 0. 17x3 plus 26x4 minus 26x5 should become 0. Okay. So by solving these three equations, we should get x1, x2, x3, x4 and x5. Okay. We'll find the values. Yes. It's continuation. We are solving equations 1, 2 and 3 right now. So second equation I am multiplying with the 26 and third equation multiplying with 10, and we'll subtract these two equations. Okay, so second equation should becomes this 182x3 plus 260x4 minus 260x5 is equal to 0 after multiplying with 26. And third equation also should becomes after multiplying with the 10, 170x3 plus 260x4 minus 260x5 should becomes 0 and should is equal to 0, and we are subtracting, so here plus will come should comes negative, and this is should get positive, and after here minus means plus term minus term gets cancelled, and here also minus should becomes positive, no, it should also cancel. Remaining term 182 minus 170, 182 minus 70, 12, x3 is equal to 0. That means x3 is equal to 0. So substituting x3 is equal to 0 in equations 1, 2 and 3, then we should get minus 3x1 plus 6x2 plus x3 term 0 is there. So remaining x3 and minus 7x5 equal to 0. Similarly, second equation x3 is 0 na, 10x4 minus 10x5 equal to 0, and 10 you should take common, x4 minus x5 should is equal to 0, and here on the right hand side we have 0, 10 should get cancelled, x4 minus x5 is equal to 0, then x4 is equal to x5. Okay, and similarly from the next equation, third equation, 26x4 minus 26x5 should equal to 0, and 26 after taking common we should get the same equation, x4 minus x5 is equal to 0. In this also x4 equal to x5 only. So any one of the equation we can consider. Okay, and from equation 4 we are taking this equation 4 right now. So in this minus 3x1 plus 6x2 plus x4 minus, instead of x5 we'll take x4, or instead of x5 we can take x4, nothing will happen. I am taking instead of x5 x4. Okay, and minus 3x1 plus 6x2 minus plus x4 minus 7x4 means minus 6x4 is equal to 0. In this minus 3 I am taking common, so what should we get x1, 3 ones are, so here plus is there, we'll get minus 3 twos are 6, so 2x2, here plus 3 twos are 6, x4 is equal to 0. So after it should get cancelled, remaining term x1 minus 2x2 plus 2x4 equal to 0. From this I am taking my x1 is equal to remaining terms I am taking on the right hand side. Okay, but general solution is nothing but x is equal to x1, x2, x3, x4 and x5. Right now instead of we have x1 value right here 2x2 minus 2x4, and x2 we didn't have, so as it is write down. x3 we have 0 right here 0, x4 and x5, x4 as it is, instead of x5 we have x4, I'm writing x4. Okay, so in this we can take here free variables x2 and x4, so you should take the common x2. Here coefficient of x2 is 2, here coefficient of x2 is 1, in third x2 is not there, 0, fourth x4, x5, so we have 0 zeros, yes na, first. Next plus x4 also you should take the common, then we should get x4 coefficient minus 2, here is not there 0, here is not there 0, here 1, here 1, so minus 2, 0, 0, 1, 1. So this means we have two vectors, this is one of the vector, this is one of the vector, so two vectors we got now. Therefore the spanning set of null space of A is nothing but, we can get the set v1 and v2, instead of v1 v2 we should write these two vectors. Okay, very important this type of problems, note this. Okay. Yeah, in this second problem, second bit let beta has given b1 b2 so on bn be a basis for a vector space V. Okay, then prove that for each x belongs to V there exists unique set of scalars c1 to cn such that x is equal c1 b1 plus c2 b2 plus so on cn bn. This is the statement has given So here let beta is nothing but b1 to bn. This is nothing but basis. Okay, this set is nothing but basis for a vector space V. So basis means it should be satisfies two properties. One is linearly independent and one more is L of S is equal to B. L of beta is equal to V. Because here instead of subspace ma beta we are taking. Okay. So linearly independent exist avali as well as L of beta is equal to linear span set. We have to it should be exist a linear span. Okay. And given x is nothing but what has given ma c1 b1 plus c2 b2 so on cn bn has given. Right now make this equation 1. We have to prove that the set of scalars c1 to cn are unique. That means I am taking, it should be exist another scalars I am choosing ma d1 to dn so that x can be written as uniquely. Here linear combination of vectors d1 b1 plus d2 b2 plus so on dn bn. So make this equation 2. From equations 1 and 2 what you are observing? So here x is equal to c1 b1 plus c2 b2 so on cn bn. Here also from the second equation x is equal to d1 b1 plus d2 b2 so on dn bn. So x is equal to, we have these two values. So we can write from these two right side terms are equal to each other. Okay. So c1 b1 plus c2 b2 so on cn bn is equal to d1 b1 plus d2 b2 so on dn bn. Okay. And you should take on the left hand side c1 minus d1 into b1. Okay, because here b1 is nothing but constant from these two. So c1 minus d1 into b1 plus c2 b2, here d2 b2 is there. After taking on the left hand side c2 minus d2 into b2 is common plus so on. Here cn bn, here dn bn is there ma. So here bn is nothing but common na. After taking on the left hand side cn minus dn into bn is equal to 0. Okay. But from the statement b is nothing but what is there? It is a linearly independent. Linearly independent means each scalar must be equal to 0. Right now? So here we are getting c1 minus d1 is one of the scalar. c2 minus d2 is also scalar. So on cn minus dn is also scalar. That means my linear combination of vectors should be equal to 0 is there. So by the definition of linearly independent, each scalar must be equal to 0. That means c1 minus d1 is equal to 0, c2 minus d2 is equal to 0, 0. Similarly, cn minus dn is also 0. Okay. So c1 minus d1 equal to 0 means c1 is equal to d1. c2 minus d2 is equal to 0 means c2 is equal to d2. So on cn is equal to dn. All scalars equal to each other. That means what ma? It has uniqueness part. Okay. So therefore the set of scalars c1 to cn are nothing but satisfies the uniqueness condition. Okay. This one is also one of the important problem only ma. Note this.